Welcome. With this video, we'll conclude our general lecture topic on the motivation for database systems. One of the things we'll be talking about is the different logical views of data, or data models. We'll also look at a few more terms. Probably been a while since we've introduced some terms. I know you're anxious to learn a few more. We'll also compare databases and files, something we've been talking about a bit already, but we'll try to give you the advantages and disadvantages of going the database approach versus using files for data persistence. And finally, we'll outline some of the major topics that will be addressed throughout the remainder of the course. So let's get going. A data model is a conceptual method of organizing or structuring data. It can be considered a way of looking at the data. The principal data models that have been in use for database include the hierarchic, the network, relational, and object-oriented. Historically, the hierarchic and the network were the first database systems to come about, and they were used largely in mainframe environments. As time went on, the relational model caught on and commercial products came out. There has been a debate or discussion as to whether the relational model is adequate for all application domains. As a result, people started investigating object-oriented, or a hybrid extension to the relational model called object-relational. The focus of this course will be on relational, but to give you an adequate background in understanding database technology, we'll give you an overview of all four of these right now. Now, each model accounts for a different way of logically structuring or organizing the data, and based upon this organization, this dictates the characteristics of how the data will be accessed for supporting database queries or inquiries, or for performing updates on the data. So we'll take a quick look at the logical structure of each of these models and describe that general nature of database access provided by each of the models. As we look at the hierarchic model, the logical organization is a tree. This diagram doesn't really do justice to the notion of a tree. I'll give you a little better perspective on that in just a moment. But the key point to get out of this is that relationships are captured by pointers from a parent to a child. So there's always a one-to-many relationship. One parent has many children. A child has one parent. Data will be accessed by navigating through the tree structure, a form of tree traversal, as you saw in data structures. As we navigate through this structure, we're always accessing a single node within the tree structure, hence we have record-level processing. Let's take a closer look at this, perhaps in practice, by looking at something we can relate to with respect to departments, courses, and classes. Let's begin by considering department. We have said that department is the root of the tree as shown here. Because the school has many different departments, we would actually have many trees and hence many roots. Let's look at one of the roots and examine the tree. We'll pick computer science. Computer science offers many different courses. Here we're showing three different courses: CSC 180, 210, and 341. 341, as we mentioned, has three sections or three classes. Those are all leaf nodes that are part of the tree, with the middle node or branch node being the CSC 341 course node. Given the tree as shown here, suppose we were interested in obtaining further information about CSC 341 section 03. We would begin by entering the tree with CSC as our root node. Then we would continue the traversal and examine the children of CSC until we found course 341. And then we would visit the children of CSC 341 and examined those until we found section 03. The network model is another mainframe era type of data model. The logical organization is that of a network where relationships are captured again through pointers, somewhat similar to what we see in the hierarchic model. Although the relationships again are one-to-many, it is possible that a node may be a member in more than one set. Hence, a child could have more than one parent, as depicted in our diagram here, by being a member in two different sets. Access is again accomplished by navigating through the structure, again following pointers, and the result is record-level processing. With the relational data model, the organization logically is that of a table. The relationships are not captured by pointers, but are captured more in a value-oriented manner by using what are called foreign keys. The many-to-many relationship can be directly implemented in a relational database. Access is through a non-procedural language where we refer to what we want based upon values or content rather than by proceeding through a navigational process. Furthermore, we achieve what is called set-level processing rather than record-level. Very significant difference, and we'll talk about this and benefits of this as we continue our examination of relational database throughout the course. So these three data models, especially the relational model, were developed to support traditional database applications. Traditional business data consisted of text and numbers. More recently, there has been interest in the need to support a variety of different types of data and applications, such as multimedia, geographic information systems, and expanding into data warehouse and online analytical processing systems, and of course the World Wide Web. Thus, we see that there may be a need to go beyond relational as we've come to know and love it over the years, working with traditional business data. And this is the reason that we'll briefly discuss the idea of object-oriented and object-relational as moving forward beyond these three classic models. The primary commercial product for the hierarchic model was a mainframe database by IBM called IMS DL1. The primary model for the network database was a product put out by Culinet called IDMS. The hierarchical and network database models were the earliest attempts to structure data according to relationships between entities. While these approaches provided a means of organizing data, they were actually quite inflexible. For example, many-to-many relationships were impossible in hierarchic databases. And although they were possible in network models using the set member relationships that we described, they were actually difficult to modify. Access to data in these systems also required embedding commands in programming languages such as COBOL. This is where we would do the navigation through the structure. Thus, they lacked an ad hoc query capability, which meant that business users relied on the IT staff to implement their requests for data access. This required a great deal of time and delayed the availability of information for business decision makers. For a relational database, there are many commercial products available. We've mentioned the ones that we list here. DB2 from IBM, Oracle database from Oracle Corporation, SQL Server from Microsoft, and MySQL, also from Oracle Corporation. For object-oriented, there have been a number of products that have kind of come and gone as people were testing the waters. Some of these include POET, O2, Object Store, and Versant. Today, the relational model is the most common. Earlier, we briefly mentioned the foreign key in this data model. A relationship between two tables is captured as a primary to foreign key association. And we reflect that in our diagram here. With object-oriented and object-relational databases, these systems follow an approach familiar to folks who have worked with the object-oriented paradigm. These systems allow for a sort of inheritance between classes and subclasses. While other models focus entirely on data content, objects in object-oriented and object-relational databases are capable of behavior. That is, they have program code. And these behaviors take the form of methods. From your experience programming in Java, C++, or some other object-oriented programming language, you should be familiar with these ideas. Finally, not depicted here in diagram form, we mention multidimensional models. These typically apply to data warehouses and are used for decision support purposes. The star schema is a typical data warehouse structure. It's still a relational database, but there are two types of tables. One is referred to as a fact table and contains numerical data that can be aggregated, such as prices, sales revenue, payments, and so on. The other type of table is the dimension table. These provide different kind of lenses by which you can slice and dice the numerical data. Examples might include customers, departments, products, time periods, and so on. The term online analytical processing, or OLAP, refers to the types of systems that use multidimensional data. And finally, we mention big data. This is an emerging concern and opportunity for business. It refers to the huge amount of often unstructured data that are increasingly important for business decision making. We talk about the V's: volume, velocity, variety, veracity, and value. These V's are big buzzwords in the big data world. We mentioned the huge quantity of data that is accumulated, hence the need for database. Let's talk about a couple terms that are used to describe these quantities of data. Kilobyte, approximately 1,000 bytes. Megabyte, approximately 1 million bytes. Gigabyte, 1 billion. And then we start to get into much larger quantities that you may have some association with in terms of on your laptop or desktop computer storage capacity in terms of terabytes or trillions of bytes. But when we're talking about databases in the real world, they start to extend beyond some number of terabytes, and we start to consider larger quantities of data, such as a petabyte or an exabyte. So as hardware capacity and processor speed have increased, so too had the demand to preserve data. And in describing database systems, in particular when you have huge quantities like in a data warehouse, a decision support system, you're not talking about merely gigabytes anymore, and not necessarily even terabytes, but additional terms are needed. In our next set of slides, we'll be considering the idea of database perhaps from two perspectives. For example, one might be, what are the benefits or advantages of using a database? The alternative might say, what are the shortcomings or limitations associated with a file system? We have a need to understand the problems or limitations associated with file systems in order to avoid problems when we design a database. Consider the quote from George Santayana: "Those who cannot remember the past are condemned to repeat it." Winston Churchill later expressed the same idea with a little bit different twist. "Those who fail to learn from history are doomed to repeat it." So let's consider what are the advantages of a database management system versus storing your data in a file system. Well, we list these here, and we'll expand on these over the next few slides. Capturing relationships. As a result of a database capturing relationships, what are the benefits? Well, we have planned data redundancy. With a file system, we usually have a collection of systems that are kind of integrated in some way, but it's after the fact. The systems have been used for a while, and it turns out that we're trying to store all of the data together, but what happens is there are redundant elements, and it was not planned. But with database capturing relationships, if redundancy occurs, it is something that we have control over. There's also improved data consistency, which is a result or consequence of reducing or eliminating data redundancy. And there's also improved data sharing, because we're putting all of the data into effectively one data store and making it available or accessible to multiple users. As a consequence of capturing the relationships, the data would not be stored redundantly in the system. Let's consider an example. The Department of Motor Vehicles. And I think I just heard moans and groans. That's not an exciting place. But if you go to the Department of Motor Vehicles, there's a license system which contains information about driver's licenses. There's a registration system that contains information about vehicle registrations. And there's also a title system associated with vehicle ownership. As three independent systems, there's a lot of overlap in the data captured in these systems. Suppose that you have a driver's license. You have a vehicle that is registered to you, and you own a vehicle. How many times should your name and address be stored? Well, if they are independent systems, that information is stored repeatedly. But the question is it stored the same way? When data redundancy occurs and you update or modify data, it must be updated in multiple locations. Suppose in this motor vehicle example, you moved, you changed your address. It would have to be changed in 3 different locations. This redundancy then leads to an inconsistency with the stored data. Furthermore, individual data items could have been stored in different ways based upon the needs that exist within these independently developed systems. And when we try to access the data, we're going to get slightly different results when we access the different systems. But by consolidating the systems and recognizing that these things interact with one another, identifying relationships, what happens is we're going to store each fact one time. If something is stored redundantly, we have control over that rather than attempting to deal with things that were designed to be independent of one another. Historically, data stored in operating system files were accessible only to those people who could write a program to access, manipulate, and format data for presentation. This meant that business users depended on the IT staff to provide such access to data. This was done in a less timely fashion. It might take days, weeks, or months for the programs to be developed and the requested information provided to the users. This is a notion of what the authors of the textbook referred to as improved data accessibility and responsiveness. Here, I've titled it Query Language / Report Generator. The idea is that most commercial databases today fall within the realm of relational, and they provide a very usable ad hoc query tool for users who are not proficient in writing computer programs. In a relational database, the logical structure or perception of data is that of a table, rows and columns. Here we give an example of what I'm calling the policy table. Notice the column headings define the attributes or the data items, and each row corresponds to one individual policy. So in a relational database, we use a language called SQL to interact with the database. There's no need to know the language of COBOL or C or Java. This language is rather easy to learn. We select Agent and Premium. Notice that these are names of columns within the table. Policy appears in the From clause, the name of the table or data source, and then to identify which row or rows are of interest to us, we put some kind of a search condition or predicate that must be satisfied, and this is expressed in what is called the Where clause. So simple and even complex queries can now be written and executed by business users without the need to rely on the availability of the IT staff. Data independence is another big benefit. The data description is not embedded within the application program. So this simplifies the programming effort because reference is made to the data item by name only, not by its location in some way. This also has a positive effect on reducing overall program maintenance costs. With a program that uses a database, the description of the physical data records would be stored in the database as metadata, not within the application. If the physical structure changes as a result of adding a new field, the application only needs to be modified if the application uses the new field added to a record. Otherwise, no change is necessary. So in general, data independence can be thought of as stating that a change in one level of the three-level or three-schema architecture does not necessitate a change at another level. Data integrity refers to the validity and accuracy of data. Data stored in a database is subject to business rules. We've briefly discussed relationships. Let's consider a simple example of a business rule. It might state that an employee is assigned to exactly one department. That is, an employee must be assigned to a department. To achieve data integrity, we store each data item in just one location. We avoid redundant updates as a result of storing the value only once. Thus, each fact is stored only once. Then, if we require a change to that fact, such as a person's address changes, so we change that fact that they live here, now they live there, it requires only a single update. The benefit is that it improves consistency of data and the reports that use that data. So additional benefits of data integrity would be we're saving external storage space. While physical storage may not be as expensive today as it was in the past, the management of that storage, such as performing backup and recovery operations, can be time-consuming and expensive. So having a smaller footprint can be another benefit. We also achieve this improved data quality. We have consistent enforcement of business rules, and integrated data are scrubbed or cleansed. What that means is if we had in one case, say a variety of file systems, and we had in one case a person was called an advisor. In another case, that same person is called an instructor. In another system, that same person is called the department chair. The idea is that different terms and descriptions often refer to the same thing, the same entity. Although data are integrated from different sources, users must be authorized to access particular data. We're putting all of the data into a single container, the database, so we want to be sure that people access only what they should be permitted to access. So the database management system uses a form of identification, authentication, and authorization as part of its general security features. Additionally, data values might be obfuscated in some way to prevent certain users from seeing the actual stored values. This protects private or sensitive data that has been entrusted to the database. So how does this work? If we look at the diagram here, the application program appears to be permitted to see the name and address. If we look at the entire record for a person, it consists of more than name and address. There's an employee number, there's medical information, and perhaps other additional information. So the application has its local view. It says, give me the name and address. It's authorized to do that, but physically stored within the record is additional information, which is filtered out and prevented from being sent to the application. Some additional benefits or advantages of following the database approach versus using file systems would be you're implementing a management philosophy. There's centralization and standardization, which makes it easier to impose or enforce rules upon the data and to control that data. So the database standards include naming conventions, data quality standards, and uniform procedures for accessing, updating, and protecting data. Thus, the whole idea of the management philosophy or perspective is to view information as a company resource. It's critical to the operation and the success of the organization or the company, so let's protect it. The DBMS use also encourages the organization to define a conceptual data model, which leads to a better understanding of the business, the data semantics that we referred to previously. Using a database system to replace an existing file system presents some potential disadvantages, which could be the idea of costs or risks associated with going this route. There are conversion costs, organizational impact, operational costs, and some element of risk. The conversion costs. Systems analysis and design now includes an additional component in the form of designing the database, understanding the application domain, and building the database. Not everyone has this skill set. So new specialized personnel may be required to design, implement, and maintain the database. Educational costs. People now have to be instructed on the use of the new technology, the database technology, which was not present in the organization previously. The cost of the DBMS itself. That's a sizable piece of software, which is quite expensive in some cases. And it's a complex piece of software. Additional specialized personnel would be people such as database administrators that would need to maintain that system. Let's take a closer look at database analysis and design as a cost. This can be a very complex type of process. Each dot in our diagram here may represent some kind of an entity. And when we look at the potential, each entity is potentially related to all of the other entities in some way. We have to gain an understanding of the application domain, the data semantics. So this means it can take some time to get a grasp on the application domain and design the database. So database analysis and design involves semantics of data items. The process produces a representation of these data items and relationships, some kind of a diagram or an illustration. To succeed, semantic information must be explicitly clear in the mind of the business user and effectively communicated to the database analyst. The database analyst who seeks to understand the application domain must acquire a clear understanding of that domain or microworld. This can be a challenging task. There's a potential organizational conflict that can arise in attempting to move from a file system to a database system. Some users are concerned that they're going to lose the power that they have within the organization because they control the file system resources in some way, or having that knowledge or understanding of that system effectively evaporates as they move to a new system. Thus, some people are not going to be on board and approve of the change, and database obviously is a big change. There are also operational costs that we've hinted at. The DBMS itself is a large piece of software, an additional layer sitting between the operating system and the application program. And this extra piece of software may require an overall hardware upgrade. The machines that were being used before may not be adequate to power this much software. Furthermore, maintaining the system is going to be a challenge. The database itself will need periodic reorganization. As far as risk is concerned, well, there will definitely be a need for backup and recovery. We've effectively put all of our data in one place. It's like putting all your eggs in one basket. And if you drop the basket, well, that's not too good. So what happens is we do need to be assured of the recovery capabilities of the DBMS. And also, we have to be sure that we're comfortable and competent in using that technology for backup and recovery. Also a concern of the vendor that you chose for the DBMS. Well, let's summarize what we're going to be doing in the course. A database management system adopts a particular data model, but must also necessarily deal with additional issues beyond how the data are structured or organized. Concurrency control, where multiple users are attempting to interact with the database at the same time. Backup and recovery, how is that accomplished? What capabilities exist with the particular database management system? Data integrity, data security. Some systems nowadays support additional capabilities like data encryption. I've taught courses on the use of that within database. And databases do it in different ways. The course that we're dealing with now will address issues related to database management systems in general, using the relational model and relational products to illustrate concepts. We'll be working with Oracle database. A major concern in our course will be the design and use of a database. So a solid foundation in the field of database is achieved through an understanding of relational database. As we wrap up our lecture on general motivation for database, let's consider what we've covered in these videos. We provided an introduction to database systems. We defined several terms that apply to database systems. We presented key characteristics of database. We explained how a database is more than simply a collection of operating system files. We introduced the three-schema architecture and explained how it is relevant to a database system. We distinguished operational and informational data management. And we explained the roles of various individuals within an organization who work with a database. We introduced the concepts for software design of SDLC and prototyping, and we discussed advantages of a database over a simple file system for storing and managing data. In our next video, we'll pick up and take a closer look at a relational database management system. We'll talk about the concepts of actually working with a system, how it operates, how we interact with it, to give you that foundation and will prepare you to get on board and actually use a database system. So get ready, and I'll see you soon.